Hi, welcome back to Free Energy Functions in Physical Chemistry. My name is Kevin Tokoph. Make sure to like the video, subscribe to the channel for future videos and notifications. So a lot of times when you're taking physical chemistry, you may be just like a chemistry major who's going into maybe a branch of medicine or something in the biological, biochemistry field, and sometimes it can seem like maybe it's not, this class isn't geared towards you. Well, there's certainly a lot of applications in biological systems, and I wanted to expose you to some of them here when it relates to free energy functions. All right, so when you talk about free energy functions, the main ones are just Gibbs free energy and Helmholtz free energy, G and A respectively. And you may notice in your textbook and a lot of times in your class, they'll start out talking about Helmholtz free energy, and then very quickly they shift to Gibbs free energy, and that's pretty much where you stay the rest of your discussion of free energy functions and beyond. We don't really deal with Helmholtz a lot, and the question is why? And we talked about that in a previous video. So with Helmholtz free energy, that tends to work best when ultimately you have a constant volume that you're dealing with and constant temperature, okay? Gibbs free energy tends to work better when you have constant temperature and your pressure is constant, okay? Now, if you think about what's easier to control in the lab, pressure or volume, well, it's a lot easier to control pressure because generally things are open to the atmosphere, right? Things are open to the atmosphere, and the atmosphere, assuming you're not going up and down in altitude, which you're not in a chemistry lab, the pressure in the atmosphere is constant. So if pressure is constant and volume does tend to change a lot depending on the container, that means we tend to want to use Gibbs free energy a lot more. All right. Now, how is this applicable to biological systems? Well, if we think about in biological systems, and when I'm talking about this, I'm talking about really for a very, very, very small change in time. Okay, I'm not talking about very long, like an entire day or something. Okay, I mean like very short periods of time, maybe a few seconds. So does temperature change? Well, temperature is maintained constant, right? That's one of the things you would learn about in a physiology course, is that the body has mechanisms to make the body temperature overall constant, and that also equates to the temperature in cells. Okay, there is an exchange of heat ultimately between the cell and outside the cell, but the temperature is kept constant. So the answer here is, does temperature change? No, temperature is relatively constant when we're talking about biological systems. All right, let me get the right brush here. All right, does pressure change? And the answer is no. All right, pressure doesn't change because we're open to the atmosphere, and there really aren't any pressure changes unless you're talking about the lungs. And that's in a gaseous state because the lungs are exchanging gases. But overall, talking about inside a cell, the pressure is constant. So the pressure does not change, okay, generally. Now, the last question here is, does volume change? Now, at first, the answer may seem like no, but the answer is yes. Recall that there's a lot of times fluid going in and out of cells, right? There's fluid going in. Concentrations in the cell can change, and that's also a function of volume, okay? And then ultimately cells can grow and shrink, and they can change shape. Certain types of cells that are, that are amoeboid in character, they can actually change the shape of their cytoskeleton and their cell membrane ultimately to move around. So yes, volume does change in cells, in biological systems. So seeing as temperature is relatively constant and pressure is relatively constant, that probably implies that delta G, or Gibbs free energy, is going to be the choice for talking about spontaneity in biological systems. And generally when you look in papers, different kinds of research papers, articles, you won't ever see Helmholtz free energy. It's not used there. And in general, in most other aspects of chemistry, Helmholtz energy is not used either very much. All right. So let's talk about why this would be. Well, we already know from hopefully previous videos that if we want to find the standard delta G at equilibrium for a given reaction, we have this very simple equation. Negative ideal gas constant times the temperature in Kelvin times the natural log of the equilibrium constant. A very, very simple equation. If you know the equilibrium constant, and that is something you can measure if you're at equilibrium, temperature is easy to measure, and the gas constant is a constant, so you can pretty easily calculate the delta G at equilibrium. But if I wanted to know the relationship between delta G and Helmholtz free energy, what would I do? Well, it turns out the relationship is dG is equal to dA plus pdV. Now you can go ahead and integrate each term here, and you get the following relationship. Delta G is equal to delta A, and the integral of pdV, if we're talking about a gas, okay, P is equal to nRT over V from the ideal gas equation, and then you just plug in nRT over V here. Now, if you're dealing with solution chemistry, and certainly in cells it's solution chemistry, this can be a little bit different. Okay, in general, for solutions, pressure is not a function of volume. We learned that in the previous video, so you could just use delta P, delta V. But in any case, I don't care what we have to use. Let's just assume nRT over V. We could assume delta P, delta V from the previous video because pressure in solution is not a function of volume for the most part, and vice versa, times dV. And if you knew this integral right here, in a lot of cases with gases, it's pretty easy to do. If you knew this integral, you add it on to delta A, the Helmholtz energy, and then it gives you the free energy. But why would you not want to do this? Why would you not want to find the delta A for a cell, for example? Well, if you think about how small cells are, how on earth could you precisely, or I should say accurately also, measure a change in volume for a cell? I mean, why would you need to do that? Why would you want to measure the change in volume of a cell? I mean, they're so small, and can you imagine the amount of instrumentation and the expense it would take to measure a change in volume? I mean, V1 to V2, I mean, can you imagine that? So why deal with delta A for measuring spontaneity when I can just use free energy and it's independent of the change in volume? Okay, it doesn't matter how much the volume changes. It's not a function of volume. Remember, Gibbs free energy is a function of pressure and temperature, not pressure and volume or volume and temperature. Okay, so recall that delta G standard at equilibrium is negative RT times the natural log of the equilibrium constant. If I wanted to express this in standard delta A, then it would have to be ultimately, and you can show this using this equation right here, it would have to be delta A standard is equal to negative RT ln of the equilibrium constant minus this integral from V1 to V2 of nRT over V dV, or this could ultimately become a dP, and you'd have delta P, delta V. We talked about that in the previous video. But in any case, you'd still have to measure the change in volume. You'd have to know the initial volume, the final volume, and for a cell, I mean, let's face it, that's pretty much impossible to do accurately. All right, so we don't want to deal with delta A. In general, for measuring spontaneity of reactions in biochemistry, that is the reason why we use Gibbs free energy. Okay, in theory, we could use delta A to calculate KEQ. We have this equation right here. We could use delta A, but measuring a change in volume of a cell is almost just stupid when we can just use delta G, and also the formula is a lot easier too in any case. So now, to give you an example of how this would be used in a biological system, let's do an example problem. And I'm actually going to do this with real numbers here, so I have my calculator right here where I'm sitting. What we want to do is calculate the free energy change, and by the way, it's the standard free energy change because we're at equilibrium, for aspartate transaminase, an enzyme with a KEQ of 6.8 at pH 7 and temperature equal to 25 degrees Celsius, which is about 298 Kelvin. Now, if you're in PChem and you haven't taken biochem, aspartate transaminase is basically an enzyme that is involved in taking amino acids, particularly in this case aspartate, and it's going to ultimately convert it into oxaloacetate. Technically, okay, this molecule right here, this is glutamate, and this molecule right here is alpha-ketoglutarate. Now, if I wanted to actually indicate what aspartate was, aspartate looks like this, okay, carboxyl, amine, and it just has one carbon short of glutamate, and it's going to be interchangeable in equilibrium with oxaloacetate, which is a Krebs cycle intermediate. Okay, you learn that in Biochem 1. Okay, both of these reactions, of course, this one is aspartate, and this one is oxaloacetate. Okay, this is basically the same type of reaction. What you're doing is you're deaminating the amino acid and replacing it ultimately with a carbonyl. Now, one thing to notice in both of these reactions, because they're homologous, notice here we lost a hydride. Okay, what is a hydride? Well, a hydride is just an H minus. Okay, how many electrons does a hydride have? Well, notice it has 2 electrons. So not only is this this is not just a simple double displacement reaction, okay? This is also an oxidation reduction, because notice glutamate here is losing 2 electrons and it's becoming alpha-ketoglutarate. Here aspartate is losing 2 electrons from the hydride, and ultimately it's forming oxaloacetate. So this is a 2 electron transfer, okay? Now, let's go ahead and calculate what the delta G would be for this reaction. Okay, so we know that delta G standard at equilibrium is minus RT times the natural log of the equilibrium constant. Now, before we do the calculation, we should go ahead and ask ourselves a question, just for a prediction. All right, KEQ, notice the KEQ we have is greater than 1, right? It's 6.8. So do we expect this to be a spontaneous or a non-spontaneous reaction at equilibrium? Well, we would expect it ultimately to be spontaneous, because when we have a KEQ of greater than 1, that means delta G should be negative or less than 0. Okay, that is, delta G standard should be less than 0. So this should actually be a spontaneous reaction as written. Okay. Also, we should say, if delta G is less than 0, what should we expect for the sign of the cell potential E, the standard cell potential? Well, if delta G is less than 0, then we should expect E cell to be greater than 0, because that also indicates a spontaneous reaction. All right, now we can go ahead and do the calculation. So what is delta G standard? It's negative R. R is the gas constant. We're going to use 8.314 joules per mole Kelvin. All right. What's the temperature? We have to have the temperature in Kelvin. The temperature we specified was 298 Kelvin. And then we're going to multiply times the natural log of the equilibrium constant. And that's going to be 6.8. 6.8. All right, and then we have to multiply all that times -1 to get the free energy change. So let's do that. So I'm going to take the natural log of this constant 6.8 first, okay? Times 298 Kelvin times -8.314. And I'm getting that this reaction ultimately has a delta G standard equal to, I'm going to approximate it, it's -4749, approximately -4749, and that's going to be in units of joules per mole. I could also say this is -4.749 kilojoules per mole. Some people may prefer you to convert this to kilojoules per mole, but certainly either one of these answers is actually reasonable. So the delta G is -4749 joules per mole, and that coincides exactly with what we expected. Delta G is less than 0, so this reaction as written is spontaneous. Okay, and we could also apply some other terms for it. It's exergonic, meaning it has a release of free energy, and that means there's an increased amount of work available in the cell around the enzyme, okay, because it's releasing energy to do work away from the system, which is the enzyme. All right, the only other thing we want to do is calculate the cell potential, and to do that, we're going to use the condensed form of the Nernst equation. Delta G standard is equal to -NF E standard cell potential. All right, I want to calculate the cell potential, so let me divide through both sides by -NF. All right, and what I get when I do that is that the standard cell potential is equal to negative of delta G standard divided by NF. All right, what was delta G standard? We just found that to be -4749 joules per mole. Okay, we're going to divide that by NF. Now, what is N? N in the Nernst equation is actually the number of electrons transferred. Well, between glutamate and alpha-ketoglutarate and aspartate and oxaloacetate, the number of electrons was 2 because we're losing a hydride in each of these reactions from glutamate. So the hydride actually ends up on a different molecule, but the 2 electrons were transferred, so this is going to be 2 moles of electrons. And then I'm going to multiply that in the denominator by the Faraday constant F. So what is the Faraday constant? F is the Faraday constant, and it's 96,485 joules per mole volt. Okay, so this is going to be 96,485 joules per mole volt. Now notice here, the joules cancels. This mole cancels with this mole. And so ultimately, I'm going to get units of volts per mole. This is going to be volts per mole. Now remember, all of this is multiplied by -1, all right, because it's negative delta G NF, and delta G is -4749. So when I multiply all this out, I'm going to get that it's approximately 0.0246 volts per mole. And that is certainly greater than 0, and that's what we expect for a delta G that's spontaneous. You should have a cell potential, E cell, that is greater than 0. Okay, and that indicates a spontaneous reaction as written. All right? So that's how you go about dealing with some of the biological things. You can calculate delta G for different reactions, delta G at equilibrium. The other thing also, remember for E cell, is this type of equation where you have the condensed form of the Nernst right here. Where did I have that? You know, delta G is equal to negative NF E cell. This is only valid when you have an oxidation-reduction reaction, okay, or at least a step in a mechanism that's oxidation reduction, because if it's not oxidation reduction, then how many electrons are transferred? 0, right? And then this formula doesn't apply. So this is only valid for redox reactions, okay? And since aspartate transaminases and transaminases in general are redox reactions, I can do that. All right, so hopefully this gave you a little bit of information on how we use Gibbs free energy in biological systems and how we don't use Helmholtz free energy in the same system. Okay, thanks for watching this. Hope it helps. See you in the next video.